day, everyone. I just want to give a brief overview of what I understand by spatial optimization and or the field of spatial optimization at least. So we are typically concerned with optimizing a problem that is of spatial nature. So what sort of problem could we deal with? Well, we could, for instance, trying to locate a set of fire stations, for instance. Okay, so that could be an example, right? Why is this spatial? Because its arrangement is spatial in the geographic sense. Could be the location of hospitals. In this case, trying to provide and optimize access to everybody while trying to minimize the cost to a certain degree. So here we have two objectives: maximize access and minimize the cost. Okay. So could have also the location of post offices. In the case where you have, for instance, government funding that is decreasing, well, in that particular case, you may want to decrease the number of post offices. Maybe in rural areas, people will drive longer distance, in urban areas, smaller distance, so you have to optimize that. Another example could be, for instance, bike share programs. Okay, where will you put the location of where these bikes can be returned to, so throughout the city. The location of schools, for instance, it's an important one, where every student should be able to be allocated to only a school, only one school, and then you're trying to minimize the number of schools that is open because you minimize the cost. So here you have a location problem, the school, and the allocation of the kids to the schools. Another example that's more in the private would be the location of cell towers. What is the objective here? We want to try to maximize the coverage. I will show an example in a second, but also so the coverage to every customer, but we're trying to keep the number of towers to a minimum because it is actually quite expensive. So in all of these examples, right, we have to make the decision of whether we open or we don't, right? So that's a decision variables, and then we also have something spatial because we're talking about the spatial sense. Now you also have problems that are space and time, right? For instance, locating, let's say, emergency services, not only in the spatial sense, but also at certain time there is a greater demand, or police officers and so on and so forth. But in this course, we're mostly focusing on spatial problems. All right, so I just gave you a bunch of examples, but there are plenty of others, as we will see through this class. Now, so when you have a spatial optimization, essentially you are trying to formulate your problem, right? For instance, maximize coverage of customers in cell towers, right? So you're trying to formulate your problem. And typically you're going to have three ingredients, I would say. The first one will be, and I rather write it this way, for me will be the objective function. What is the problem we're trying to do? Are we trying to maximize the profit? Are we trying to maximize the access? Are we trying to minimize the cost? What is it that we're trying to do? Okay, that's very important. Second, you have decision variables. Okay, now, sometimes they are a little bit more complicated, but in general, it's pretty straightforward. So in our case, in optimization is, are we going to open or not a particular facility? Maybe a hospital, okay? Maybe a school, maybe a post office, name it, okay? So that's the decision. We're going to make a decision on this. It's going to be a 0 or 1, right? It's not going to be a 2, a 3, or 4, or 5. Yes, we may open 2, 3, 4, 5 post office, but at a particular location, we only open 1, okay? And then you have typically constraints that are going to limit the problem. The constraints, for instance, could put upper bound on the budget that we have for schools, could be putting a constraint on how far a particular cell tower can cover people, maybe 5 miles at the most. Maybe can put a limit on how far people are willing to drive, maybe to go to a coffee shop, or maybe to go to a specialty shop or something, right? And then you also have the constraints that are typically integer, so 0, 1, or 2, or 3, or 4, or binaries and so on. Those are other specific set of constraints. And so the structure of this particular formulation is as follows, right? So first you would probably define the decision variables, right? So I'll put them here, decision variables, okay? That's important to do that up front. So for instance, right, you could say xi, okay, equal to 1. Let's say if we open at 1, at I, and 0 otherwise. That's just a very generic example. I'm not saying that this is what we're going to use. Sometimes we are going to use x, sometimes we would use y, sometimes we have different sub-indices, as you will see later on. But that would be typical. The second would be then the objective function, so that would be a maximization, right, or a minimization, depending on what it is, or maybe a combination of both, and those are called multi-objective or bi-objective functions and so on, right? So for instance, if we were trying to minimize the number of facilities that were open, then we would do minimize and then the sum here of I of all of the xi. There could be a bunch of other characteristics, like the cost, for instance, or maybe the importance. I mean, there are so many different parameters that can characterize these axes or this location. And then you would have subject to, right? And so for instance, you could also say, let's say the sum, right, should be less or equal than, let's say, 3. So what it is, for instance, in this case, there could be only 3 facilities that are open, and then at the end you would say xi belongs to 0, 1 if those facilities would be integer, so open or closed. So you have the problem here, decision variable, objective functions right here, constraints, and then you have the second constraint, which are called integer constraints. All right, everybody. So I'm just want to quickly illustrate here the point I was trying to make. Let's assume for a second that we are trying to locate some cell towers. Okay. So I have a large study area. I hope you can see it here. Okay. And I'm going to consider a few potential locations. So I'm saying, okay, maybe I can locate a tower here. Maybe I can locate a tower here. Maybe I can locate a tower here. Maybe one over there. Okay. Now that means that we have, I would say here, 1, 2, 3, and 4. Okay, so we have x1, x2, x3, x4, and the question is, okay, if I can select 2 of them, which one would they be? Now, if you think about this for 1 second, the number of combinations is pretty high, right? So you could have 1 and 2, that could be one combination. You could have 1 and 3, you could have 1 and 4, you could have 2 and 3, you could have 2 and 4, and then you could have 3 and 4. So you have here 6 different combinations, which is quite a bit. And let's suppose for a second that this here represents, okay, so I'll just try to keep it pretty straightforward here. Let's suppose that this kind of represents the coverage of that particular cell tower, so that would be a sort of range, if you wish, okay, right here. Okay, run one more here. Okay, one more here. Right, and this is of course approximate, as you can see, but that's okay. You will understand the concept, that idea of this coverage. Now, okay. So if I now tell you briefly that the majority of the population, right, lives, let's say, over here. We have big pockets of population over here, and then maybe some pockets of population over here. Okay, which location would you choose? Probably 2 and 3, because they would cover the most amount of people. Okay. If the population doesn't matter, then you can choose which one, whatever you want, right? But x1 covers a little bit outside. We don't really need that one, so probably it's less desirable. x2 is good, x3, x4, and so on. So what are the objectives that we're trying to do is an important decision. And when you can see that the number of combinations is very high, so even if I had a fifth one, that would be much more complicated. That's why we're going to use optimization technique. We can now just evaluate all the possible solutions.